proof technique. Proof technique called induction.
Mm-hmm.
And the volunteers. Yeah.
Yeah.
And I'm going to share. So first I'll talk a little bit about the theoretical concepts in induction, and we will have a look at some examples. Full form notebook. I'm giving up all the space in free form. I thought it goes infinite to any direction. Only
Yeah, in theory.
thing that can maybe use for each. Anyway, actually, if we move on, now we got some space. Here comes some space. And today we're going to talk about induction.
Do you want to just use maybe your mic and I'll turn this one off because then we'll be able to hear you better on the recording.
Sure.
Cool.
My Mac. There we go. I think that should be good. Okay. I can write here induction. Okay, it's a proof technique. It's called induction. Have you guys heard of proof by induction before? Sounds familiar.
Like-
Some high schools teach it.
Inductive reasoning.
Yeah, inductive reasoning. And it's used very common in reasoning, automated reasoning, or interactive reasoning techniques. So, a few sessions ago, we talked about natural deduction, and natural deduction included a lot of the common proof techniques we use very often, right? So we talked about proof by contradiction. So that was one of the common proof techniques, and there's a rule. There's an inference rule in natural deduction that is essentially proof by contradiction. And the way we write this rule is essentially you assume the opposite of what you want to prove. All right, so you have an assumption, you assume the opposite of what you want to prove, not A. And you do some reasoning from your assumption. And if you derive contradiction, then you can conclude that A is true. All right, you prove what you want to prove. So this is a typical proof by contradiction in natural deduction. There are also other proof techniques covered by our usual reasoning rules. So the other ones are called proof by contraposition. So it's a very similar word, but it's not the same idea. Proof by contraposition says if you want to prove A implies B, and it's really difficult to go from A to B, that direction is really difficult. Alternatively, what you can do is you can assume that not B is true, and then you prove that not A is true. Right? So not B implies not A is called the contraposition of A implies B. And these two are actually logically equivalent. So if you can prove the other one, it's as good as proving A implies B. Okay, so there are some proof techniques directly, that directly comes from our logic and reasoning techniques. But the one we're going to look at today is somehow special, right? So it's not really defined in our logic. and it's not really in our proof system, but it is one that we use very, very often. It's called induction. And we use it very often because a lot of the concepts defined in mathematics and also defined in your programming languages are defined inductively. All right, so I think today we'll give two examples. Example number one is natural numbers. Okay.
Is it just like your 1, 2, 3?
Yeah, natural numbers. So how is natural numbers defined? Any ideas? How would you define natural numbers?
Regular, just numbers without symbols and things. That kind of.
So there's a mathematical definition of that. It's a mathematical definition. I think last week or the week before, I talked about Peano's arithmetic, and it involves the definition of natural numbers. So we can search for it on Wikipedia. Peano's arithmetic. So it's got a bunch of axioms about arithmetic. Let me see if I can find. It's got to be, oh, there we go. So you see, rule number 1, 0 is a natural number. And rule number 2, for every natural number, it equals itself. Actually, so 2, 3, 4 are just some properties about equality. 5, so the axioms 1 and 6 are actually the definitions of natural number. So it says 0 is a natural number, and for every natural number n, this S of n. So S is called the successor function, right? So it gives you the successor of n. Effectively, in your usual mathematics terms, S of n is essentially just n plus 1. Okay, so it says if n is a natural number, then n plus 1 is a natural number. All right, so
Basically any whole positive number, if it's 0,
yeah,
and then Sn.
Essentially, but if you can see there are two cases in the definition. All right, so two cases. The first one is called the base case. The base case gives you the foundation. All right, base case says 0 is a natural number. And then there's an inductive case. Inductive case says if n is a natural number, so is the successor of n. I'll just write n plus 1. All right, and with these two definitions, it covers everything. It covers 0, 1, 2, 3, 4, 5, 6, 7, 8, goes all the way to infinite. Okay, so this is called an inductive definition. So it has a base case. That's where things start. And it has an inductive case. It says, I define the kth step, and then I give you the k plus 1 step. That's inductive. And not just natural numbers, a lot of things in mathematics, in computer science can be defined in this way. So I'll give you another one that we use very common. Let's call it a list. Okay. So in your programming language, I think in data structures, you probably learned linked list. So this is an example of list. Okay. So how do we define the data structure list inductively? Well, if it's an inductive definition, it's got to have two parts. It's got to have the base case. It's got to have the inductive case. So what would be the base case of a list? Where do you start?
There's a first item.
Before the first item, you have an empty list.
Oh, right, of course, yeah.
All right, so an empty list. So we say empty is a list. Okay, that's the base case. What would be the inductive case? So it says, let's say if I'll call it access is a list. Okay, if access is a list, then you append one more thing to the list, you still have a list. All right, so it's actually very similar to the definition of natural number. So if access is a list, then you append another element to it. Let's just say this is the operation of appending x to the list access is a list. Okay, that's inductive definition. All right, and you can do the same for a lot of other data structures. Let's say a set. We can define a set. Empty set is a set. If you've got a set, then you union with another element, it's still a set. All right, so you can define all sorts of different data structures inductively. And this sort of inductive definition is also closely related to recursion. All right, so you can see this, it's sort of a recursive definition. All right, it's a recursive definition. And in fact, if you look at our very early definitions of logic, okay, for where do we have? Maybe just right there. I think it's just here. So our definition of the syntax of propositional logic, you can also define that inductively. So what are the base cases? So you have here you have more than one base case. So base case, a base case would be a formula that you cannot break it down to smaller formulae. All right. So top is a formula, you know, or bottom is a formula, or any proposition, let's say any proposition P is a formula. You cannot break those formulae down to smaller formulae. All right, so those are the base cases.
It's basic building blocks.
Yeah, most exactly. All right. And you have the inductive cases. So the inductive cases would say if, let's say A and B are formulae, so are A and B, A or B, A implies B. You can also have not A. All right, so these are the common ones that we've talked about. Okay, so this is also the inductive definition. So the definition of A and B, A or B, A implies B, not A, depends on the fact that we assume that A and B are actual formulae, and then you can build more complex formulae based on what you already have. All right, so it's inductive definition. So essentially same thing here. All right, you have access is a list, and you can build a larger list. If n is a natural number, you can build a larger natural number. All right, so a lot of things can be defined inductively, and then when we prove something about something that can be defined inductively, we can do proof by induction. Okay, and proof by induction naturally has two cases. The proof has two parts. You have to prove the base case. You have to prove the inductive case. All right, so let's say if we want to prove a property, let's say prove a property P over natural numbers. If you want to prove a property P over natural numbers, doesn't matter what the property is, any property over natural numbers. If you want to do it inductively, then you've got to prove two cases. All right, so base case is that you need to prove that your property P holds for the natural number 0. Okay, that's a base case, because natural number 0 is the base case of the natural numbers. And second case is an inductive case. Okay, so inductive cases assume that your property holds for the natural number n, any n, given any natural number n. Assume that the property holds for n. You want to derive that the property also holds for n plus 1. Okay, so if you can show that P of n implies P of n plus 1 combined with the base case, then you can conclude that the property holds for any natural number. All right, so that's inductive proof. That is inductive proof.
Kind of saying like this thing works for this base case, but it's only like true in all cases if it works for like. No, that was my train of thought. That's not making sense. Sorry.
So I mean, you can think of it this way. So what base case establishes is that the property holds for natural number 0. Yeah. Right, and then you can apply the inductive case. It says if it holds for 0, then it holds for 0 plus 1, which is 1. Okay. So the property holds for 1.
And then if it does, then we can say yes.
And then you can say it also holds for 2.
Yeah.
All right, and then you can apply inductive case again. You can say it also holds for 3. It also holds for 4, etc., etc. It actually holds for any natural number you have. Yeah. All right, so this is base case, and those would be the inductive cases.
Right. Okay.
All right. And then if it holds for all those natural numbers, then it holds for any natural number you like. Yeah. So it holds for any natural number. Okay, so that's a very powerful technique. It's a very powerful technique. And it's useful if you want to show some property holds for some data structure that may have infinitely many cases. Yeah.
Like natural number. To do every single one to check and prove, you can kind of use this logic to say if it works for these, it will work for the rest.
Exactly. Right. So yeah, you only have to do 2 cases instead of doing all of those infinitely many cases.
Gotcha.
Okay, so we can have a very concrete example. Okay, so this example comes from the mathematician Gauss. Okay, so I'd say he's probably one of the smartest guys in the history of man. He's extremely smart, and you can probably find something related to Gauss in basically everything you do on the computer. Even you go to Photoshop, there's a blur technique called Gauss blurring, Gaussian blurring. And if you do statistics, there's Gaussian distribution. It doesn't matter what you do. There's something that Gauss has developed. And this guy is like crazy smart, genius.
I wondered where the Gaussian blur comes from, because I was like, maybe it's like it looks a little like gauze because it's kind of fuzzy. But yeah, no.
So so he's extremely smart, and urban legends say so. This is urban legend, right? So I don't think there's evidence to back this up. So take it with a grain of salt. So when he was, back in his days, probably they had a very different education system. It's probably similar to primary school today, right? And his teacher asked everybody, all the students in the class, can you sum up 1 plus 2 plus 3 plus 4 ... until 100? What is What is the result? Sum everything up from 1 to 100. What's the result? All right, so everybody started to do the summation, 1 plus 2, and then plus 3, plus 4, plus 5, until they go to 100. Okay, and this is actually a very easy problem for us now, because we know that there's a way to sum this up, right? So, you know, Oh yeah. So you're getting there. So what is the equation? So let's take the example from 1 to 100. All right. So first number plus the last number multiplied by the number of items. Yeah, so that's 100 divided by 2. All right. So that is the formula that we use to sum up this series. All right. So legends say Gauss, that's invented by Gauss when he was doing primary school. Right? It's crazy. It is crazy. Okay, so he actually generalized this to the series 1 plus 2 plus blah 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 until n, or it doesn't matter what n is, and the summation is going to be 1 plus n times n over 2. Okay, so it's a summation of this series. So you can prove this. I can prove this by induction. So how do we prove this by induction? Let's say if we want to do it by hand, we want to show that this is correct. We want to show that he didn't make a mistake. Okay. So, well, we need to have a base case. The base case is this is correct when n is 0. Okay. So when n is 0, basically what you've got is that series is just 0. There's nothing on the left-hand side. And on the right-hand side, you have 1 times 0 over 2. That's 0. So base case is okay. All right. And because this series is a bit special, so you can actually extend it to 0 plus something. It's the same. All right. So it's just that part is omitted because we don't really need that part. Okay. What about inductive case? So it says that you assume that this summation equation holds for a natural number n. You don't care what n is. Okay, so you assume that 0 plus 1 plus up until n is this. You assume that it holds for n, and you need to prove that it also holds for n plus 1. Okay. Times. You need to show that it also holds for n plus 1. Okay. So we just need to prove this equation here. And when we prove this equation, we're going to use our assumption. Okay, so how do we do that? Well, let's go from the left-hand side. N plus 1. So that's the left-hand side. So what do we know? Well, based on our assumption, we know that this equals 1 plus n times n over 2 plus n plus 1. Okay, because this part is equal to the left-hand side there. So we can just replace this part with the right-hand side there. So that's pretty straightforward. And then what do we do? Well, so we're going to say this guy is 2 times that over 2. That's the same. All right, so we're not changing anything there. So we can move this up here and say, this is what we've got. All right. And then let's expand with what we have here. So this is n plus n squared plus 2n plus 2. Okay. And that is what? N squared plus 3n plus 2. And that equals n plus, well, that equals 1 plus n plus 1 times n plus 1. All right, so you can try this. What is 1 plus n plus 1? So this is n plus 2. What is n plus 2 times n plus 1? So that's n squared plus 2n plus 2 plus n. Yeah, so that is what you have here. Okay, it's the same. It's what you have there. Okay, and then this is an inductive case. So we've shown that it works for the base case, works for the inductive case. Therefore, this holds for any natural number n. Okay, it doesn't matter how much you want to add up, it always works. Okay, that's proof by induction. And the reason why I want to talk about this is not that easy to automate. So what I'm going to do is I'm going to go to the board. So it's a bit boring if we only do writing on the board. So it's good if we look at some applications. All right, so okay, so what I'm going to do is I'm going to log in this Teams from my computer as well. So yeah, I think I'll transfer to this device. And we'll stop there. Okay. And okay. So to move this a little bit. Okay. I think my screen should be up there, but let me share my screen again. Okay, so I share my screen. And this is Isabelle Hall, and it's automatic. It's called an interactive theorem program. It can do a lot of things automatically, but when it comes to inductive proofs, it needs a little bit help. So let's look at one example. Right? So if you want to prove something sort of straightforward, let's think of something about natural numbers that are not so hard. Okay, so if we want to say let's say we have two numbers, x and y. And if y is greater than 0, then x plus y should be greater than x. That should be, it's pretty easy, yeah?
Yes.
So y is greater than 0, then what do we want to have? X plus y is greater than x. That's got to be the case. Well, we need to define that y is an integer, y is a natural number. Otherwise, there might be counterexamples for other number series. So we say y is a natural number. And for something as simple as this, you don't need to do much. You can just go by auto, and it just proves it. All right, so it shows you that this is a theorem and everything's okay. It's already proven. You don't need to do anything. But we can actually define what we did just now by hand using some piece of program. So it's almost like we're doing programming. And then we want to prove that our program is correct. Okay, so this is somehow analogous to a field called program verification. So you're writing programs and you want to prove that your program is correct. All right, so as opposed to do testing, so you don't want to test. What if it's, you know, incorrect when the input is 1? What about input is 2? What about input is 3? Right, so formal verification says, okay, we're going to do some proof, and we're going to prove that it is correct once and for all. Okay, so here's the idea. But first, we need to write the program. And the way I think automated reasoning tools, and especially logicians write programs, is they're going to use functional programming. That's the most common way when doing things in theorem provers. And it's a bit different than you do programming in an imperative language. So in imperative language, it would include, let's say, probably everything you've used. C, C++, Java, Python, you know, they're all imperative languages. So functional languages work in a slightly different way. Works in a way that they don't do those kind of flows step by step, right? So you wouldn't have loops, for instance. But if you want to do loops, you can. You just do recursive functions. You just call the function itself. So it achieves the same thing. So, you know, last week we talked about computability. So from a computability point of view, they are equally powerful. So whatever you can program in imperative language, you can program it in functional language and vice versa. It's just sometimes it's easier to do in one language than other languages. Okay, so we're going to have an example of a functional programming language that does the summation. Okay, so I'm going to give it a name. I'll call it add to n. Right? Call it add to n. You can name it anything. It's just the name of the function. And I'll need to define the type of the function. So when you do imperative programming, you also define the type of the function. You define the type of each argument, and you define the return type. All right, so here you do the same. Except I write it in a specific way. So what I write here says I need 2 arguments. So everything before the last one is the type of the arguments. All right, so this is a return type. The return type is natural number, and it takes 2 arguments, and those 2 arguments are natural number. Well, actually, wait, it only takes 1 argument, I think. So the summation, all we need is the natural number n. All right, so it only needs 1 argument. So it takes a natural number as input, the n, and it gives you the summation from 1 up until n. All right, so this is the input type, this is the output type. It's a type of the function, and this function is defined as, well, we sort of do it in 2 cases. One is the base case, one is the inductive case. Okay, so we say if n is 0, then the result is 0. Okay, so that's the base case. What about the inductive case? So we say with n plus 1, and here it's called the successor, well, success of n. Success of n is just n plus 1. So if we want to add onto the successor of n, this is defined as you first add onto n, right? You first add on up until n, and then you also add this number here. All right, so that's the recursive definition. If you want to go 1 plus 1 adding up until n plus 1, you first add add from 1 to n, and then you add n plus 1. All right, so this is a recursive definition. So this function is supposed to do the summation for us. And now we want to check if the function is correct. Okay, we want to check if the function is correct. So if we do add to n of n, then we would expect this should be equal to something over 2. Well, I think in Isabelle Hall, it's a division, something divided by 2. And the something is 1 plus n times n. Better bracket this. This is the equation that we talked about, right? So this is supposed to be correct. And well, so here it says this is, you have one goal that you need to prove, and we can apply things like auto, and it's not going to prove it. All right, so here it's not so trivial. It's not like this one. You apply auto, it's done. All right, so here you apply auto, it doesn't do it. And Isabelle Hall also comes with a tool called Sledgehammer. So it calls some sort of AI engine, and it does automated reasoning with the help of AI, and it tries to do it. And it probably can't do this easily. So I can try this tool, we can wait. And I'm not sure if it could give us anything. Okay.
Was that first part essentially like defining the base case? The second part is asking it to do the inductive reasoning.
Yeah, so see, you see this kind of inductive or recursive definition, it calls for inductive proof.
Okay.
Right. So instead of relying on this, it's probably going to go forever.
Yeah.
So we're going to prove it. And we're going to help the theorem prove a little bit. We're going to give it something, and then we see how it goes. So we're going to say we want to do an induction on the natural number n. All right, and automatically it's pretty smart these days. So you want to do an induction on n. I'm going to give you a template of doing that. So I can click this and it generates a template. Template says this is a base case of n is 0, and there's an inductive case of success of n. Let's look at each one of them. So to look at base case, so what we want to prove is this thing holds when n is 0, right? And this is pretty easy. So now the automatic technique can do this. So now this one's done, it's trivial. And then we have the inductive case. So inductive case, see, it's exactly the same as what I wrote by hand. So we assume that it works for n, then we need to prove that it also works for n plus 1, the success of n. And now when you break it down to this, so the automatic proof technique can do it. So this is done. All right, so this is called interactive theorem proving. So the automatic tool can't easily do this, but as long as you help it a little bit, and then it can do it. All right, so now we've proven that, this piece of program that we wrote about summing up a series of natural numbers it is indeed correct. It doesn't matter, what n you give it as input it's always correct. Okay, so program verification. We can have another example. So we talked about lists. So we can have some operations on a list. So what sort of program we can write about the list? We can do concatenation of two lists. Concatenation of two lists. And we can do it in functional programming. I just call it cat. And the input is two lists. The output should be one. Right, that's how you. So I'm going to write something like this. All right. So this prime A just says it is a list of any type. It can be a list of natural numbers. It can be a list of integers, it can be a list of real numbers, and whatever other data structure, it would also work. All right, so this prime A is just a placeholder for a type to be instantiated. So it takes two lists. I mean, they've got to be of the same type, and it combines them into a list here. All right, so that's the syntax. So we're going to define this function, and we're going to do it inductively, but we're going to do induction on the first list. All right, so if the first list is empty, second list, I call it y's, the outcome should just be the second list because the first list is empty. Yeah. And inductive case, so if the first list is a list XS with a head element X, okay? And YS is the second list. So how do we do the concatenation? So you want to use recursive definition. So this is probably what you want to do. So you concatenate the rest of the list with YS, but this head element should be up here at the beginning. Okay, so you put the head at the beginning and then you do this recursively. You do this recursively until XS is empty and then it's finished. So it's like a loop. Okay, so this is a piece of program that we wrote that concatenates two lists. And we want to verify that it actually does what we specified it to do. So we're going to write a property about this function, and we're going to say this function given two arguments, the output is supposed to be the concatenation of these two. So that's the syntax at is a concatenation. All right, so the output should be the concatenation of these two lists. And again, if you want to try the automated tools, or if you want to apply things like auto, it just won't work. It's not good enough. So we need to give it a little bit help. We want to say, well, because the definition goes induction on the first list. So here we're going to do induction on the first list, which is XS. But the only tricky thing here is, while we are doing the reasoning, we want to say the second list can be anything. So we basically want to, we don't want to consider that in the reasoning. All right, so we only want to do induction on the first list, not on the second. So I'm going to say the second list is arbitrary. Okay, and it's pretty smart. It generates template, so I just need to follow the template. And as you can imagine, the base case and second case can be proved by the automatic proof techniques. All right, so it is proven that this piece of program is correct. It does what we specify. So if you do this in another way, let's say if you concatenate XS with YS, but you put the head element somewhere here. So this hash, it only works when the left-hand side is an element and the right-hand side is a list. So it doesn't work if the left-hand side is a list. All right, so if the left-hand side is a list and we want to concatenate them, we need to do this. But as soon as you change this definition to do that, you'll see that this doesn't work. All right, it says it can't prove it. So because this program is not correct. If you do it any other way, I mean, there are probably other ways that are correct, but this is one of the ways that are correct. Okay. Yeah.
So makes sense and good enough to put it into its own
Mhm.
words.
So this is so I just wanted to give you a flavor of program verification. It's going to do programs. and you can reason about the program, so you can prove that it is correct. Right? And it is correct no matter what sort of input you give to it. So that's the beauty of program verification. Absolutely.
Yes, we know that whatever you put in here.
Last week, did I talk about this an example of rocket launch, right? So in 1990 something, Ariane 5 is a rocket developed by the ESA, the European Space Agency, goes up to the sky, and after 20 something seconds, explodes. And the reason was there was an integer conversion that is converted was causing integer overflow. Things you don't want in the program. So in applications like that, you want to make sure your application is absolutely correct. Right? It doesn't matter what input you give to it, it's got to behave correctly. And that's where they cannot afford to have mistakes, and no amount of testing is enough. So they have to do this kind of verification. So formal verification is used widely in mission critical applications in industries, defense, aerospace, engineering. And interestingly, recently, so there's talk of Web 3.0 on the horizon, and a lot of applications in Web 3.0 are based on blockchain. A lot of them are used to deal with a large volume of transactions. Okay, so I had a chat with a lead engineer at Alibaba. So they're basically the Amazon in China, and they've got their own blockchain system, and they deal with billions of dollars every single day, right? And it's based on blockchain, so they need to write smart contracts to do the transactions. And being on the blockchain, if you deploy your smart contract on the blockchain, you can't change it. If it has a bug, it's going to be there forever, right? So they realized, whatever they're doing in Web 3.0, it's not enough, right? So in Web 2.0, you make a website, and you know that different browsers going to interpret your code, and different browsers even going to display in different ways. So some things won't work, some things are going out of the places, but that's completely fine, right?
Yeah.
That's completely fine. Yeah. We can put up with that. They cannot afford to have a mistake in smart contracts. So they're saying they need formal engineering engineers. They need formal verification engineers. They can't find enough graduates to do the job. There aren't a lot of people who are doing this. So yeah, so they can't find enough people with the formal verification background, but they're thinking, with Web 3.0, this is going to be a big market for these kind of jobs. There's just not enough talents. So yeah, this is pretty much it for today's content. As something extra, it'd be interesting to think about this kind of summation, right? This kind of summation of natural number or integer series. See, this function sums from let's say 0 up until a specific natural number n, right? This is an interesting question, and this is not something I'm going to prove, but I'm going to write it here. What is 1 plus 2 plus 3 plus up until infinity? Okay, up until infinity. And this is a different question than asking what is 1 plus 2 plus 3 up until a specific number. All right, so here you want to sum up the whole series of natural numbers, goes up until infinity. And then a lot of tools that we have in mathematics suddenly stops working. All right, it stops working. So you cannot use that equation anymore. It doesn't work when you want to do it to infinity.
Is there an equation that does work? Can work?
There's actually a specific result.
Okay.
And you'd be very surprised to learn. I mean,
like infinity plus the equation.
Nope. You'd be very surprised to learn that if you add everything up to infinity, well, actually, so first, I guess, I think this is this summation is really difficult to do. And there might be different results given by different people. Okay. But one of the, it's very tricky. It is very, very tricky. But one of the commonly recognized result is -1/12. Right? It's going to break your mind. It equals -1/12. So you'd be surprised. Why would it even be minus? And why wouldn't it be this? So it is something that you're going to be surprised to learn how this works. So see, operations that involves infinity often breaks, a lot of tools we have in mathematics. A lot of things don't work. And the proof is actually not too hard. It's just some manipulation of the series. But I won't be able to do that in 2 minutes.
That's okay, yeah.
All right. But it is related to another series, which is a lot easier. And you can probably see it in 1 minute. So it's 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc., etc. Okay.
That's 0.
Say, a lot of people look at this and they go, oh, you see, if I bracket it this way, right, that would be 0. But if I bracket it another way, what if you bracket it this way? Right?
It ends up 1.
And it ends up 1. All right, so that would be 1. So it depends on how you bracket it. It actually gives you a different result. So mathematicians were mad at this. They were like, how can I get different results when we bracket it different ways? This just doesn't make sense. So somebody came along. So somebody came along and said, okay, I'm going to say this whole series equals capital S. Okay, it equals capital S. And then what happens if I do S? S plus S. All right, so you're getting there. Yeah. You're getting there. So you can do your own manipulation. Yeah. So if you do all that manipulation, you actually find out this equals 1/2. This actually equals 1/2. So based on those results and some other results, you need some more, manipulation. You'll eventually find out 1 plus 2 plus until infinity, it actually equals a negative number.
Well,
So you can actually find out some links here. It's this one here on Wikipedia. It equals -1/12. Okay. And it also talks about the easier ones, this one. So the proof to this one is pretty straightforward. So you can just follow that. And that just equals 1/2. And how come it doesn't make sense? But that is math. So yeah, so what we proved there in Isabelle-Holland works for a specific number. It doesn't work for the summation up to infinity. Alrighty, I think that's all for today's session. And see you next week.